In this episode, we are going to see how you can control the flow and execution path of your program using the selection statements in Java. From a very long time, selection statements have been the backbone of implementing Boolean logic in programs. In fact, they are so fundamental that in all my years of experience, I can't recall encountering code that didn't rely on selection statements, except, of course,
the Hello World program.
we will cover everything you need to know about selection statements what, why, where, and how in this episode. And do stick around till the end of this video as we will see how the core logic of a real world video media player can be implemented using the selection statements in Java. Hi everyone, my name is Harsh and welcome to the Coding Ikigai. I'm a software engineer at Oracle and I'm passionate about sharing my knowledge to help people find their niche and their Ikigai in the world of programming. You are currently watching the Core Java Programming series, a completely free, in-depth guide designed to know everything there is about the Java programming language and to get you industry ready. If this video helps you in any way, don't forget to smash that like button and leave your thoughts in the comments down below. So without any further ado, let's get started. In the last episode, we talked about how statements form the building blocks of a program. These statements help us shape the core logic of our program and make them executable. To simplify the idea of problem solving in Java, you can think of any program as being made up of three main phases: the input phase, the processing phase, and the output phase. Let me explain that to you with an example. Pay close attention to the details over here because we will build on top of this for the future sections of this video. Imagine that we have a triangle and the length of its three sides are given as side 1, side 2 and side 3 respectively. Now let's say that you want to calculate the area of this triangle based on the sides. Mathematically, you can use Heron's formula which you can see on the screen over here. But the real challenge is figuring out how to implement this programmatically in Java. As always, we start by creating a new Java file, and inside that file we define a public class with the same name as the file itself. Compute triangle area in this case. Then we add the main method which serves as the entry point for the program where the execution will begin. This is just a quick recap of what we have covered in the previous episodes. You can find the link above to revisit those topics in detail. Now first up, there's the input phase where you set up the groundwork. This is where you declare and initialize your variables, maybe prompt the user for some input data, define some constants like pi or epsilon, and generally gather all the info that you need to get rolling and produce the final output or result. In our example, we are taking the input of three sides of the triangle. We will be storing these inside the variables of double data type named as side 1, side 2 and side 3 respectively, as you can see over here. And just like that, we complete the first phase, that is the input phase. Next up, there's the processing phase. This is where the real action happens. Here, your code does all the heavy lifting that it needs to do. It takes all the input that you stored in variables, all those constants, applies some logic or calculations on them, and transforms it into something entirely new and meaningful. This phase might involve multiple steps of calculations and transformations, which often generates multiple intermediate values along the way. In our example, the processing begins by calculating the semi-perimeter of the triangle first and storing it inside an intermediate variable of double data type with the same name. Then, using the semi-perimeter and the triangle side length, we apply Heron's formula, which we already saw, to calculate the area and store them inside a variable, again of the double data type. And just like that, your processing and the calculation phase is done. And last up, there's the output phase. This is where all the hard work that you have done pays off. After the dust of processing has settled, it's time to show your results to the user. This is where you take the transform data, add any final touches, and maybe package it with some extra information like the overall execution time or something, and ultimately return it to the user. In our example, we take the calculated area, append a descriptive message for clarity and beautification, and display it directly on the console. In software engineering, whether it's a simple script or a massive web application, everything revolves around this three-phase cycle of input, processing, and output. Even the APIs that you interact with daily on the browser follows the exact same pattern. A user sending an input to an API, like a request to fetch all their Instagram posts. The API then receives the input and forwards it as a request to the backend server. This is where the processing phase kicks in. The backend server handles tasks like authentication and authorization, fetches the requested data from the database, and prepares it in a usable format, such as a JSON response. Finally, the processed data returns to the API as a response, and further, that is sent back to the user interface or your beautiful UI, where it's displayed on the screen to the user. But now, let's come back to our program for computing the area of the triangle. What if you needed to calculate the area of 1,000 such triangles? Would you sit and rewrite the same code 1,000 times? Well, if you are thinking about it, then that's a very trippy idea. Or let's say that you want to calculate the area only when the sides entered actually form a valid triangle. Is that possible? How can you conditionally execute a set of statements in Java? Or what if your processing phase becomes too big and cluttered with complex calculations? Wouldn't it be better to refactor it by taking the logic of the area calculation, putting it somewhere else, maybe call it something like compute area, and then simply refer to it when needed? That way, your main method stays clean and easy to read. In all these scenarios, we want some way to collect and organize the statements into a group such that we can perform collective operations on this group instead. Does Java provide a way to glue multiple statements together in one single unit? A block is essentially a way of grouping multiple statements together between balanced curly braces so that they can work together as one cohesive unit. It's Java's way of enabling us to repeat, conditionally execute, or maybe structure your code in a clear and organized manner. Think of it as a tool for grouping statements to work together harmoniously, giving our program a better structure and readability. In Java, we essentially have two main types of blocks. Mandatory blocks. These are named blocks that Java requires to define core structures like classes or methods. Without these blocks, the program wouldn't even compile. For example, every class has a class block that groups the data and the methods of the class together as one single unit. In our case, that block is named as compute area, and you can reference it later elsewhere for code reusability. Similarly, every method has a method block that groups the statements of the method together into one single unit. In this case, the method block is named as main, which is the most common method that we have seen till now. And again, you can refer them anywhere by just calling the main method. Then we have custom or optional blocks. These are unnamed blocks that you create yourself either to structure your code for readability purposes or to logically group certain statements, link them, and define certain group actions on top of it, like repeating this block 1,000 times or maybe conditionally execute this block. For example, in this case, I'm enclosing the processing and output phase of our code in one custom block. In this episode, we will focus on how to conditionally execute your code blocks using the selection statements. Normally, the code in your Java source files is executed in a straightforward top to bottom sequence, just like you're reading a book. Control flow statements allows us to break out the straight execution flow and dictate how our program should behave under different circumstances by making use of decisions or selection statements, loops, and branching statements on certain blocks of code. Now, to truly see and understand the flow of a Java program better, let me introduce you to an amazing visual tool that's widely used in software engineering, the control flow graphs. It's essentially a diagram that maps out all the possible execution paths a program can take during its run. In fact, CFGs are super useful in software testing, especially for things like finding code coverage or spotting any unreachable code in your program. But we will hold that thought for now and come back to it later in future episodes. For now, let's focus on creating our first CFG for the compute triangle area program. Here's what we do. We start by numbering all the statements in our program, starting from public static void main, which becomes the first statement, and then working our way down to the closing bracket of the main method block, which becomes your last statement, that is statement 6. A control flow graph is a directed graph. That means we represent the program flow using nodes and edges. Here's how it works. We create a node for the entry point, which is where the program starts, and assign it the number 1. Then we draw a directed edge representing the flow towards the next possible statement in your program, which becomes node 2 in this case because it's a straightforward program. We keep on connecting these nodes following the program flow until we reach the very last statement. At that point, we create an exit node marking the end of the program. Neat, right? And this brings us to the first rule of creating a CFG. Every statement in the program becomes a node in the graph. We also include two extra nodes, one for the entry point and one for the exit point, just so that you can make it a single entry and single exit program and we do not create any confusion. All these nodes are connected by directed edges, which represent how the program flows from start to finish. Let's step up now. At their core, selection statements rely on two things, either a Boolean expression or the value of an expression to decide which path your program should take. Now, there are two main schools of thought here. The first one revolves around using Boolean expression. This approach includes a variety of tools like one-way if statement, nested if, two-way if else, multi-way if else statements, and conditional operators. On the other hand, we have the second school of thought, which uses the value of an expression to control the flow of your program, which is the switch statement. We will first see how Boolean expressions, which are expressions that evaluate to either true or false, are used for altering the paths of your program. A one-way if statement in Java is a conditional statement that allows you to execute a block of code based on the results of a Boolean expression. If the expression evaluates to true, the code within the if block is executed, otherwise it is skipped. The syntax of a single if statement is as simple as it gets. You write if, followed by a Boolean expression, and then enclose the block of code which you want to control using your curly braces. Easy, right? But let's understand how it works with the help of a control flow graph. We start by numbering the statements in our program. Let's say we number them from 1 to 4. Node 1 represents the statement just before the if block and acts as the entry point for the program. Next, we move to node 2, where our Boolean expression lives. This is what we call a decision point. Think of it as a checkpoint where the program pauses to ask a question. Should I execute this piece of code or should I just skip it? Since it's a Boolean expression, there are only two possible answers. If it evaluates to true, we take the yes path, execute node 3, which is the code inside the if block, and then proceed to node 4 to exit the block completely. However, if it evaluates to false, we completely skip the if block, that is the node 3 in this case, and go straight away to node 4 and exit. This is how a simple one-way if statement alters the flow of your program. Pretty neat, huh? And that brings us to the second rule of drawing a control flow graph. Every decision point becomes a branching node. The node will have multiple outgoing edges, each of them representing a possible outcome of that decision which you take at decision point. For a Boolean expression, it's always two outgoing edges, one for true and another one for false. Alright, let's apply this to a compute area program. Right now, the program doesn't check if the triangle is valid before calculating the area. That's not an ideal situation, right? So let's fix that. We will add a condition to ensure that the area is calculated only if three sides of the triangle are non-negative. But that is a mathematical requirement. We need to translate this into a logical statement first so that our computer can understand. This is where Boolean expressions come into picture. The requirement basically means that side 1, side 2 and side 3 should all be greater than or equal to 0, and they will be connected using a logical AND operator, as we want all three conditions to be true before calculating the area. Let's plug this requirement into our code block and see its control flow graph. We begin by numbering all the statements from 1 to 7. 1 is the entry node. We declare all our variables at node 2 and then reach the first decision point at node 3 where our Boolean condition is evaluated. If that results in true, we calculate the area and display it on the console by executing nodes 4, 5 and 6 and then exit the if block at node 7. Whereas, if it results in false, then we skip the area calculation entirely and go straight away at exit at node 7. And voila, you have added your first selection statement to the program. A one-way if statement performs an action if the specified Boolean condition evaluates to true. However, if the result is false, nothing is done. But what if you want to take alternative actions where the condition is false? You can use a two-way if-else statement in that case. The actions that a two-way if-else statement specifies varies based on whether the condition is true or false. The syntax for adding an else block is super straightforward. The if block stays the same, but now you add an else block right after it. This lets you specify what should happen when the condition evaluates to false. Let's see that with a CFG. We begin at node 1, which is the entry point, and our flow reaches the decision point at node 2. If this evaluates to true, the program follows the same flow as before. It executes node 3, exits the if block, and finally terminates at node 5. But if the condition evaluates to false, instead of doing nothing as we were doing before, the program executes the else block, that is node 4 in this case, and completely exit at node 5. Now let's incorporate this beautiful idea in our compute area program. Let's say that now we want to inform the user if they have entered an invalid triangle by displaying a message on the console. The Boolean expression stays exactly the same. However, now we have this else block which takes care of it. From the CFG, we can see that we begin at node 1, and when the flow reaches the decision point at node 3, if it evaluates to true, we calculate the area and show it to the user, same as before, and exit at node 8. But now, if the condition is false, the program skips the if block, it goes to the else block to show a custom message at node 7 before exiting. And that's it. Nested if statements in Java are simply if statements within other if statements. They allow for more complex decision making by providing the ability to test multiple conditions in a hierarchical manner. Each inner if statement is executed only if its outer if statement condition evaluates to true. Here's the basic syntax of nested if statement, where at line 4 you can see that there's an inner if statement tucked inside the outer if block on line 2. To understand this with a CFG, we begin from node 1, reach at first decision point at node 2. Node 2 deals everything inside the green box. If node 2 evaluates to true, the program executes node 3 and reaches node 4, the inner decision point inside the blue box. If node 4 evaluates to true, the program follows through to node 5, completes the inner blue box, exits the green box, and finally terminates at node 7. However, if node 4 evaluates to false, the program skips the blue blocks entirely and goes straight away to node 7 to exit. And if the outer if, that is the node 2, evaluates to false, the program completely skips both the green box and the blue box inside it and execute the else block and exits away at node 7. You can have as many levels of nesting as needed to accommodate your program's logic, but a lot of nested if statements can become harder to read and maintain if overused. As you can see, the control flow graph itself is becoming very cluttered. It's essential to keep the code structured and clear whenever you are writing the program. Let's bring this concept back to a compute area program. Now we are adding another important validation rule. The sum of any two sides of a triangle must always be greater than the third side, a classic rule from trigonometry. To implement this in code, we create a Boolean expression. Side 1 plus side 2 should be greater than side 3. Side 2 plus side 3 should be greater than side 1. Side 3 plus side 1 should be greater than side 2. Basically all possible combinations. And we combine all three conditions with a logical AND, since all of them needs to hold true before we evaluate the area. This logic will now be applied to our core area calculation. Our program is now modified to take care of the requirement. Let's see that in action. We enter the program at node 1, which is our starting point. At node 2, we initialize the variables. From there, we hit the outer if decision point at node 3 to validate non-negative side lengths. If this condition passes, we move to the inner if decision point at node 4, where we validate the sum of the sides. Here's where the flow diverges. If node 4 passes, meaning that the triangle is valid, we execute the logic for calculating and displaying the area at nodes 5, 6, and 7, and then exit from both the inner and outer if blocks at node 10. However, if node 4 fails, that is the sum of the sides is invalid, we skip the calculations entirely and displays a message informing the user and then exit at node 10. Similarly, if the outermost if condition at node 3 fails, implying that one of the sides had negative side lengths, then the program bypasses all further logic, displays a message for invalid input, and exits at node 10. And there you have it, the working of nested if statements in Java. The multi-way if-else statement, or if-else-if ladder, is a series of if-else statements that provide multiple alternatives for the execution of code based on the evaluation of multiple conditions. Here's the syntax for the same. It's useful when you have several conditions to check and you want to choose exactly one out of several possible alternatives. The control flow graph starts at node 1 and evaluates conditions sequentially from top to bottom. At node 2, if the blue condition is true, the block executes and the rest of the ladder is skipped. If false, the flow moves to the next condition at node 4 and check the condition. If true, execute the block and skip rest of the ladder. However, if it is not true, then it goes to node 6 and repeat the same process. This continues until a condition evaluates to true or the program reaches the end where it exits. And that brings us to the final requirement for our compute area program. Once we have validated that the triangle is valid, we want to inform the user whether the triangle is equilateral, isosceles, or scalene. The logical Boolean expressions for these classifications are shown above over here, and we can incorporate this logic into the program using a multi-way if-else statement as shown over here. We won't create a CFG because I think we have gotten enough hang of it and it will be very complicated, but I hope you get the idea of how a multi-way if-else statement works. In Java, the question mark operator, also known as the ternary conditional operator, is a shorthand way of writing an if-else statement. It is the only ternary operator in Java, meaning it takes 3 operands. The general syntax of ternary conditional operator is Boolean condition, followed by a question mark, followed by an expression 1, colon, expression 2. I would like to pause here for a second and clarify something important. This is an operator and not a statement. What does that mean? Just like the addition operator, for example, 2 plus 3 returns the value of 5, this operator also returns a value of a specific data type. However, it cannot be used on its own. It needs to be assigned to a variable or used in an expression to form a complete statement. Here's how it works. If the condition is true, the value of the expression 1 is returned. However, if the condition is false, the value of the expression 2 is returned. The same rules of precedence, associativity, and type conversions are followed in evaluation of the expression that we have discussed in the last episode, so do check it out. The conditional operator is often used as a compact way to write simple conditional statements. For example, this is how a simple if statement to find the maximum between two numbers can be converted to a single line using this conditional operator. It's particularly useful when you want to assign a value to a variable based on a certain condition. In this example, if x is greater than y, the value of x is assigned to the variable result. If x is not greater than y, which is the else case, the value of y is assigned to the variable result. And you can see that over here. The result is then printed out. Ternary operator can make code more concise and increases your readability. You can also use nested ternary operators to create more complex conditional expressions, but it's important to use them judiciously to maintain code readability. Here's an example of a nested ternary operator to find maximum between 3 numbers. While the ternary operator can make code more concise, it's essential to ensure that the code remains clear and understandable. Sometimes using a traditional if statement might be more readable, especially for complex conditions like in this case. As you can see over here, the conditional operators are making things more cluttered and unreadable. And that completes our discussion from the first school of thought. Let's now move to the second school of thought, which uses the value of an expression to split the flow of your program. In Java, the switch statement is a control flow statement that allows you to select one of many code blocks to be executed based on the value of a variable or expression. They help in providing multiple possible execution paths for a program, unlike the if-else statements, which only provides 2 paths, that is either true or false. Java switch statements can be used in place of a if-else statement to write more cleaner and concise code. Let's break down the rules of working with a switch statement. Here's the basic syntax of a switch statement. To understand it better, we will number the statements and use flow graphs for visualization. We begin with the keyword switch, followed by a switch expression in parentheses. This basically signals to Java that the switch block has started. This brings us to the first rule. A switch expression is just like any other expression. For example, var1 plus var2 multiplied by 29. It follows the standard rules of precedence, associativity, and type conversion during its evaluation and produces a result of a fixed data type. For instance, the expression might evaluate to 350, an int value. However, the switch expression must always yield a value only of char, byte, short, int, string, and an enum data type. Let's move on to the case statements. In Java, the keyword case marks a decision point inside a switch statement. signaling that some action needs to be performed over here. In our example, there are 3 decision points: node 3, node 6, and node 9. But what's the action that we need to perform over here at the case statement? The action is to match the value in the case statement with the value of the switch expression. We will basically check whether value 1 is equal to the value of switch expression or not. This brings us to the second rule. If a match is found, the statements starting from that case are executed until a break statement or the end of the switch block is reached. For example, if the match happens at node 4, we execute the block and exit at node 5 when we encounter a break. If the first case does not match, we simply move to the next case and check again. If value 2 matches the switch expression, we follow the same rule, execute the statements, and exit on encountering the break. And this process keeps on repeating for all the values until we reach the final case value, that is value n, as shown over here. But what happens if none of the cases match? This brings us to the third rule of defaults. The default case, which is optional, acts as a fallback which performs actions when none of the specified cases match the switch expression. It's a very special block that ensures that the program doesn't just skip over the entire switch statement. But what are these value 1, value 2, and value n that we have been seeing throughout? Let's talk about the fourth rule of switch statement. Value 1, value 2, and value n, all of them are unique and constant expressions or values, and they must have the same data type as the value of a switch expression. For example, if the switch expression evaluates to a value of 97 with byte data type, then a case value can be 34 of byte data type, but it cannot be 190 because Java expects a byte here, and the range of the byte is from -128 to 127. So that is out of the range of byte capacity. Similarly, a value can take a constant expression of the form 2 plus 10, which is basically 12, but it cannot take a non-constant expression like 9 plus x because it cannot know what value it has at compile time. A case value can also not take the value of 30 plus 4, which is 34, because we have already used it in the case 1 above. And it cannot be Apple as well because that is a string data type and byte type was expected. I hope the rules are clear from the examples above. Let's play a game. The rules are simple. If you choose 1, it's rock. If you choose 2, it's paper. And if you choose 3, it's scissors. We start in the main method and initialize the variable number to 1. Next, we reach the switch expression and begin matching the cases. First, we check if the value is 1. If it matches, the program prints rock and exits. If it doesn't match, we move to the next case and check if the value is 2. If true, we print paper and exit. Similarly, if unmatched, we go to value 3. And if matched, we print scissors and exit. And if none of the cases match, we go to the default case and print not a valid choice. In our example, the program takes the blue path because the number value is 1, so it prints rock on the screen. But what happens if we don't put a break in switch statement? Oh, the tragedy. So here's how it plays out without break. We start by evaluating the switch expression. Let's say it matches case 1. Great. We reach node 5. But here's where things get interesting. Since a break statement is not encountered, once a case is matched, the execution doesn't stop there. Instead, it cascades running every statement from that point onward until the very end of the switch statement. So after matching case 1, we don't just stop at rock. We end up printing paper, scissors, and even the invalid choice. Every statement gets executed whether the subsequent cases match or not. Now let's flip the scenario. Suppose case 1 doesn't match and we move on to case 2. If it matches, the same rule applies. It prints paper, scissors, and then not a valid choice. If case 2 is unmatched, we go to case 3, and if it matches, we end up printing scissor and invalid choice. Even the default case gets executed. It's like the floodgates open once a match is found and every statement downstream gets executed. This is referred to as the fall-through behavior. And that was the fifth and final rule of the switch statement. So be careful and apply breaks appropriately, else your program will derail. Let's now bridge the gap between the abstract programming concepts we have been exploring and their application in real-world scenarios through a real-time video media player. A video media player is a software designed to play video and audio files, and you have likely encountered several of them like the open source VLC media player, Apple's QuickTime player, Windows media player, or even the media players on YouTube and Netflix. While we won't dive into the intricate workings of these big robust systems, We will capture the essence of their functionality and build our own custom Ikigai video media player using Java and JavaFX, showing these concepts. Picture this: a sleek custom media player screen with buttons like play, pause, reset, forward, and backward. Now, these buttons aren't just for show. Each of these buttons are like a butler standing ready to respond the moment you press them. When you press play, the button says, "Hey, the user wants the video to start playing." Hit pause and it politely signals, "Stop, let's freeze the moment." Reset rewinds the video to the very beginning, while forward and backward jumps the video ahead or pull it back by 5 seconds, giving you the full control of things. But here's the real challenge. How does a media player know what action to take when you press one of these buttons? That's where the magic of buttons and events comes in. Before we dive deep into that, let's first understand how buttons or any UI related elements work in general in JavaFX. When you click a button, it triggers what's called an event. This event is like a signal, a message that says, "Hey, I have been clicked." In Java, you can define specific actions for these buttons to decide whenever an event is triggered. Once that event is captured, the media player can decide what to do. The decision-making process happens through something called event handlers. These handlers are basically methods or functions that are designed to execute specific actions, like playing a video, pausing it, or jumping ahead. They are the ones that take your signal and convert them into action. In JavaFX, we link these event handlers to buttons using a method called setOnAction. In our case, all the buttons are connected to a single method called handleMediaAction. Now, this is where the switch statement becomes the star of the show. The event handler is completely based out of switch statement. Each button corresponds to a distinct case in the switch statement. For example, case play starts the video. Case pause freezes the action. Case reset asks the media player to reset the video to the beginning. Case forward skips by 5 seconds ahead, and case backward rewinds by 5 seconds. The switch statement is like the control tower of this particular program. It directs different commands to the right action. This approach significantly simplifies the logic and keeps your code very clean and organized. But wait, there's more. As programmers, we are always enhancing user experience, and our media player is no exception to that rule. Let's talk about toggling themes between dark and light modes. With a single click, you can switch between a sleek modern dark theme and a classic bright light theme. It's a small addition, but it makes a big impact on usability. Now, how does the program know whether to turn on the dark mode or revert back to a light mode? The toggle theme button has an event handler that calls the toggle dark mode function. A boolean variable is dark mode maintains the current state of theme on UI. If that variable is true, we are in dark mode, and if it's false, then we are in light mode. Every time we call this method, it flips the state of this boolean variable and asks a custom method to apply the theme to all the objects. The if block loops over all the buttons and all the functionalities and paint them according to the dark theme, whereas the else block does the opposite of that. And just like that, the theme is seamlessly switched with a simple toggle. Usually on websites, this is done by just switching the reference between light and dark HTML and CSS files that you are referring to. So the next time you watch a movie or listen to a music on a media player, take a moment to appreciate the hard work of selection statements. All the source code is now available at GitHub, which you can find in the description down below. And here's a quick cheat sheet that you can refer for creating control flow graph. And that's it for this episode. We recently hit 150 subscribers on YouTube, and I want to extend a heartfelt thank you to everyone who has been a part of this amazing journey. If you enjoyed my explanations with all those animations and graphics, please consider giving this episode a like and share your favorite part in the comments down below. And don't forget to hit that subscribe button and ring the bell notification so that you never miss out on an update.